Hello and welcome to part 2 of AQA Physics Paper 1, higher tier 2018 series. Can zoom in a little bit. Oh, maybe too much there. Okay. Another student did a similar experiment. Okay, so this was carrying on from the irregular measurement of the chest piece in part 1. Okay, so this is moving on from that. So another student did a similar experiment. He determined the density of 5 common plastic materials. Table 1 shows the results: acrylic, nylon, polyester, polystyrene, and PVC, so polyvinyl chloride, and density in kilograms per meter cubed. So figure 4 shows the results plotted in the bar chart. Okay, density and material. So complete figure 4, you should write the correct scale on the y-axis and draw the bars for polyester, polystyrene, and PVC. So I might have to get my straight line thing out in a minute. Okay, it's fun. That's a good thing to do in paint as well. Okay, so we need to have to actually be able to draw it, we need to put the axes on, don't we? Acrylic. So that's what acrylic was, 1,200. Okay, so it needs to be 500. So let's have a look. So 500, 1,000. That's not that, is it? So density in kilograms per meter cubed. Let's try and work out what it is. So 100, 200. So it could be 500. Okay, so. Okay, nylon's on there. Nylon's 1,000. So that'll be easy one. This is part of the process, just trying to work it out, isn't it? So it actually looks, yeah, it was what we said actually, wasn't it? So that's, each big square represents 250. So 250, 500, 750, 2,000. Okay. Right. So that's each one. Let's put the axes on to show you. Let me just saying it. Let's put the axes on. There's a bit of a tricky one. A tricky one to figure out. Right, so let me just won't do tech, I'll just write it on for now. Right, so yeah, up so halfway is 500. 500. We've already got the unit. 250. It's not very clear. 250. 750 and 1,000. Okay, so it's like there, and there. 0 is 0. Start at the origin. Right, so we need my straight line. You need to rule yourselves in this bit. Okay, I don't want any messy graphs because yeah, it's supposed to be drawn with a ruler. That's what a ruler. So we need to put polyester on next. So polyester. 1380. So if each one of those is 250, what is each tiny square? So it's made up of 1, 2, 3, 4, 5. So 250 divided by 5, each one represents 50. So it's like 50, 100, 150, 200, 250. So each tiny square represents 50. So if that's 1380, so what's the width there? It doesn't matter too much about the width. We want to be approximately equal. Okay, so it's 4. The polyester in the middle, so it's let's have a look how many squares is each side. 53. So it's 1, 2, 3. It's all about, so when you do your exam paper, it'll be easy because you have it right in front of you on the computer screen. Right, so that's 1,000, like nylon, 1380. So you go all the way up to 50. Okay, then so that's one. So let's see, sort of like that's 1250. 1300, 1350. So it's just going to be just under 140. So it's 1 fill the other one in. Same height. Ooh. Okay. Polyester. Polystyrene 1040. It's only going to be a little bit above this one. Okay. Yeah, an exam you probably tell it's going to take you a little bit longer than other questions. So maybe you want to come back to this one if you think it might take you a while. PVC is the easy one. 100. Which one's 50? Maybe 2 up. It's going to be higher than the other one. Not as high as polyester. Complete that graph. Filled in a little bit that one, so being a perfectionist. Okay, so yeah, it's not too difficult if you've got a ruler, but it's working out the scale there. Okay, so that's 4 marks for doing that, so it's not too bad. Okay, for 4 marks. I'm going to open the next one up. Next page gets in paint, so I need to open it up. Right, so let me just zoom out a bit again. Zoom out. The student, that's carrying on, the student is given a piece of different plastic material. The student determined the density of the material 3 times. Table 2 shows the results. The density in kilograms per meter cubed, so still talking about density. Okay, determine the uncertainty in the student's results. The uncertainty. So the biggest one is 1120, smallest is 960. Okay, so uncertainty is the difference between the biggest and the smallest. Okay, so it's 1. Let me just go back to put my pen back. Put my pen back on. Right, so 1120, the biggest minus the smallest, 960, and the average of those two. Just give it, that's maybe 120. Let me just rub that up. It's a bit unclear what's going on there. So we do that. So 120. Sorry, 1120. 1120. Okay, minus 960. Okay, and divide it by 2. Let me get my pen back again. Okay, and that gives us 80. And that'll give us 2 marks. Oh, nothing more on that page. Let's open the next page. Just AQA, sort of like one question, and then you've got a lot of blank space. Whereas other exam papers seem to be a bit more scrunched together. At least you've got more space to do things. But sometimes it kind of gives you the impression the answer is a bit longer than it really is. I would think, but then you look at the number of marks, only 2 marks, so 1 for working, 1 for the answer. That's a good guide there. If there's only 2 marks, it's probably not going to be very long. Right, let me zoom out again. Okay, question 3, a different question. Figure 5 shows a diver. The diver is using a canister of compressed air so he can breathe underwater. Which 2 sentences describe the movement of air particles in the canister? So 2 sentences. So let's have a look. It says they vibrate about a fixed position. Remember the gas. Okay. They move in random directions. The motion of all the particles is predictable. They move with a range of different speeds, but they move in circular paths. So this is the gas. I keep reiterating that because it does make a difference what state something's in. So let's have that. So they don't vibrate about a fixed position because that would be solid. They move in random directions. That's true. So this is tick. Okay. So the motion of particles is predictable, not in a gas. They move with different speeds, that's true. Not all the same speed. They move in circular paths. There's no reason why they would do. Okay, so it's those two. The temperature of the air inside the canister increases. What happens to the movement of the air particles? So if the temperature of anything increases, the speed increases, because temperature is really a measurement of speed of the particles. So, and it would be a bit more precise, the average or the mean, going to be a bit scientific today, it's a science paper, the mean speed of the particles increases. Okay. The mean speed of the particles increases, and we've been told because the temperature increases. Can we open the next page up? Okay, so we'll zoom out again. It could be dangerous if the temperature of the air inside the canister increased by a large amount. Okay, explain why. I'm sure everyone actually knows why this is. Okay, but just to explain it. So if the temperature increases, so as temperature increases, the pressure increases. Okay. Pressure increases. If this gets too high, it could explode. Okay. So if you see anything like a deodorant can or hairspray with warnings on it, it should have all have warnings, so you don't put them anywhere near fire or a radiator, because this is the exact reason, because they're compressed gases, okay, and if they get too hot they can actually explode. Okay, let's have a look. A canister of air was tested to find out how the pressure changed when it was used by a diver. Air was allowed to escape from the canister. We got the canister and let it escape, so it vented it. Remember, venting prevents explosion. Okay, the pressure of the air in the canister was recorded every 5 minutes for 80 minutes. Figure 6 shows the results. So pressure in megapascals. So that big M is mega, and time in minutes. So if you think about it, we have to make sure the units there. Okay, megapascals. So estimate the atmospheric pressure. Okay, so estimate. So be where you think about this. So look at the scale again. So this is the thing about scale, isn't it? So it seems easier as it may initially be. So it seems easier than it initially is because of the scale. So 0.5. So each one, 0.6, 0.7, 0.8, 0.8. So each of the tiny squares represents 0.1 megapascals. Okay, so it was vented for quite a long time. So it says estimate the atmospheric pressure. Okay, so it's when it goes to the lowest. This is quite a nice graph. So this is it goes to 0.1 megapascals. Okay, 0.1 megapascals. So let's have a look at the next page. You might have to go on to part 3. We'll have a look at it. I don't want each part of the video to be too long. Okay, so we'll have a look at this one. So divers can safely stay underwater until the pressure of the air in the canister has reduced to 25% of its original value. Determine the maximum time the diver can safely stay underwater. Use figure 6. I'll bring that up again in a moment. Okay, so all the pages here. We kept them. Right, so the original pressure. And the original pressure was 2.25. Okay. Let's put that, so write that down. So original pressure. What we're going to do is kind of a fault trail. 2.25, and that's megapascals, units there. Okay, so we need to work out 25% of that. So it's 25% equals the same way, we'll work that out the same way I did the other percentage earlier. So 0.25. Okay, and that gives 0.56. Right, that's not the end of it, because that's it, because this means we've got to remember our train of thought here, so let's go back 0.56. Okay, so let's go across. So let's get 0.55. So it's a little bit above there. And you have a pencil and a ruler, draw across. Okay, so between 20, so it's 22, 4, 6, about 27 minutes. Yeah, I can say that because it depends a little bit. What's that? 27 minutes. Drawn with it properly with the pencil and ruler. So 27 minutes. Okay, so what I'm going to do is stop the video there, and I'll see you in part 3. So thank you for listening. See you in part 3.